system. I used the circle construction to determine the working area for both RRR and RPR. Because for the RRR system, each branch they have length joined by the length issue is from 0.3 connected by the revolute joint. So the branch vary from 0 to 0.6 meter. Then we can find the large circle showing here. To find the working area for the RRR parallel manipulator, it is highlighted by the shading, include the lighter and the darker part. That's working area for the RRR parallel manipulator. I have a separate picture showing right here. But for the prismatic joint, because the prismatic joint have a lower length issue, it is from 0.3 meter to 0.6. So because of the length very smaller, so the working area is small down. It's showing right here. It's in the center part, darker with the darker shading. And here is the separate picture. To accommodate the trajectories, we redesigned the prismatic joint. Suppose we have a relative length. The relative is all relative to the revolute joint, and the relative will allow the prismatic joint have a capable length issue from 0 to 0.6 meter. So this redesigned prismatic joint allow the RPR parallel manipulator to have a consistent working area with the RPR parallel manipulator. And the chosen trajectory are circle trajectory, spiral trajectory, and the large radius of arc trajectory. And they are reachable, inside of the working area for both RR and RPR parallel manipulator. And the chosen trajectory are representative for the actual cutting path. And for the further trajectory, it could be formed from this chosen trajectory, and it's easy to derive. For my experiment, I choose they have a 100 Newton force always acting on the manipulator and effector, and it's always opposite to its motion, and it will always tangent to the trajectory. So in this slide, I'm going to introduce how do we find the range intensity solution. Well, first, let's consider the non-redundant actuation for the both RR and RPR. We will actuate the base joint or the elbow joint. If we actuate each base or elbow, we can find the basic equation for the force. We can find the equation showing right here. This is the force equation. It is sum over the actuated joint J and the branch I, and with the range intensity multiplied by the associated reciprocal school. We could rewrite this equation into a matrix equation. We can form the actuated joint associated reciprocal school into one matrix, multiplied by collect all the range intensity into one vector. We can rewrite this equation showing right here. To solve this equation, we can find the range intensity of the actuated joint and use the torques equation. We could find out the applied required torques for the actuated joint. Here, inside of the brackets, it is a mechanical advantage, and the circle star, it is a reciprocal product related to the actuated joint. So here have the performance evaluation for the non-redundant actuation. We have 4 examples showing right here. The figure on this side, it is actuated the base joint of RR parallel manipulator and elbow joint for the RR, and this is for the base joint for the RPR, and this is actuated the prismatic joint for the RPR system. By this evaluation performance, we can see all the curves are crossing line 0, and that is the moment if they crossing line 0. That's the moment to allow the backlash occur during the operation. And we can see the magnitude of each curve around over 100 Newton meter Newton. So it's not good. We have to apply a large force or torques, but we do have a backlash problem for each actuated joint. Well, let's consider the redundant actuation. If we actuated the base joint, elbow joint together, so what's the performance? If we actuated all the base joint, elbow joint, so for one system, we will find 6 different actuated joint. Each actuated joint, we will find the associated reciprocal screws. They can form a 3x6 matrix. This 3x6 matrix is showing right here. The first 3 are involved with the base joints and elbow joint. They are 3x6, 3 are corresponding to the 3-dimension force capability, and 6 are corresponding to the actuated joints for base and elbow. And we collected the range intensity from the vector showing right here. To solve this equation, we use the Regnal-Taylor pseudo-inverse solution. It will give us the minimum true norm solution, so the smallest required torques or force. And we can see this is the result showing here. I'm showing one case. We did the same experiment for the other 2 trajectories as well.